Hi everyone, welcome to this quick recording on Schrödinger's equation. The point being today is I want to find some sort of a rationale for Schrödinger's equation, which is normally written as for a one-dimensional particle in quantum mechanics as this expression basically. So we need to find some sort of a reason for why it is the way it is. Now you have to understand what I'm about to do is not really a proof of Schrödinger's equation, but rather a justification for it. So we really need to understand where it comes from in a sense. Okay, so we're trying to build a rationale for it. Its value is not really for its the way it is or for where it comes from, but rather for what it does for us. So whatever we make out of it, that is really the main thing. The function psi that I am writing in here for the case of a one-dimensional particle is time and of course space dependent, but it represents something that we probably need to talk about in a separate video. So this is really the bulk of the whole thing, is trying to find this function, which is called the wave function. So again, this equation describes the wave behavior of a particle or the wave mechanics of a quantum particle, namely an electron or proton or a combination of them. Okay, quantum particle. So when I say a particle, I mean M. Quantum most likely involved H, Planck's constant. Mechanics is some sort of a dynamics involving energy and positions and momentum and all of that stuff. So let's see where it comes from. That's the whole thing. That's the whole point in here, or at least some sort of a rationale for it. In classical waves, in a normal wave, okay, it has two things. It has a frequency and it has also a wavelength. These two quantities are connected to one another via the dispersion law, where these two are equal to the speed of the velocity v. Now, normally we express them in terms of frequency or wavelength, or alternatively I could express them in terms of other quantities, omega, which is just 2 pi times f. This is called the angular frequency. This is a convenient way, and you will see why that is. And actually same thing for the wave number, which is 2 pi over lambda. So we can express this too. Instead of using frequency and wavelength, we can use k and omega. So in this case, if I take the dispersion law and multiply both sides by f and divide by f, I mean 2 pi, I'm sorry, multiply by 2 pi and divide by 2 pi. So this is equal to the same quantities because 2 pi over 2 pi is 1. This is omega, and this is 1 over k, because k is 2 pi over lambda, so lambda over 2 pi is just the inverse of k. So I can write this expression, the dispersion law, as omega equals to kV. So this is how the angular frequency and the wave number are connected, as opposed to how the wavelength and the frequency are connected for the same wave. Normally, a wave is described by the wave equation, which can be written as 1 over v squared, the time derivative of whatever is oscillating. In this case, let's call it psi. So for the case of sound, it's probably the pressure. For the case of string, it's probably the position up and down. And for the light, is either the electric field or the magnetic field, and so on and so forth. So this is the time dependent is equal to the space derivative. Again, I'm taking the one-dimensional case. Namely, this psi still depends on x and t only. And v is the velocity of the wave. And that's how we got this expression. Actually, we got it off of the wave equation. We want to achieve something similar. We want to come up with something similar. Obviously, this is the goal. This is what it's going to look like for the case of wave mechanics. So, here is the point. For the case of normal waves, Mr. Planck introduced this connection between the frequency and the energy of the wave in order to explain the the black body radiation. So for that case, I can write the energy of light in this case, or the electromagnetic waves, as just dividing by 2 pi, again in terms of omega, and multiplying by 2 pi. In terms of omega, this quantity is just omega. And of course, h over 2 pi is a new constant, which I'm going to call h bar. H bar is just by definition h over 2 pi. And h is Planck's constant, 6.626 times 10 to the negative 34 joules second divided by 2 pi, which is roughly about 6.28. So this is about 1.05 or something like that times 10 to the negative 34 joules second. So it's just another constant that physicists use, and you will see this combination of h over 2 pi happening a lot. That it's actually much more convenient to kind of shorten the writing in terms of h bar, that's all. So that's how the energy is written. It's the same h bar that you see in Schrödinger's equation at the end of the day. So it's the same thing divided by 2 pi. So that's how the energy is expressed in terms of the angular frequency. So for light, in order to understand the black body radiation, must have an energy that is proportional to the angular frequency, omega. Furthermore, due to the photoelectric effect and also Compton effect, those are the two phenomena that we explored so far, light can be thought of as a particle called a photon, whose momentum is actually equal to h over lambda. And that then can be expressed in terms of the wave number just by doing something similar, multiplying and dividing by 2 pi. This is h bar, and this is now the same thing as I was talking about all along before, namely k, 2 pi over lambda. So this is h bar k. So good. So right now we know that light can have a particle behavior by having a momentum and also having its energy, and both of them are proportional either to the wave number or the angular frequency. Mr. de Broglie suggested, and later on of course it was used, that particles also do the same thing. Particles exhibit wave behavior, behave as waves. I mean, running an electron through a double slit experiment, you will see that electrons will interfere. So that is the point in here. Therefore, they must have also an omega and a k, an angular frequency and wave number. So their energy then for a particle must be h bar omega if they're going to be behaving as waves, because that's what waves do. And we know that a particle has actually a momentum that is mass times velocity, and have their energy, in the case of a kinetic energy, at least as equal to 1/2 of mv squared. Now if I take that quantity v from this expression and sub it in there, therefore the kinetic energy of a particle is equal to 1/2 of mass times velocity squared, and velocity is p over m, so it's p squared over m squared. Cancel the m squared with the m, and we can write the kinetic energy of a particle as just p squared over 2m in terms of its momentum instead of its velocity. Now we're going to discuss from this point on free particle, meaning u is equal to 0. There is no potential. Particle is free, it's in space, so its entire energy is just that of the kinetic energy. Therefore it's equal to p squared over 2m. Remember, if it were to be a wave, its momentum also must be equal to h bar k, because it has a wave number. Therefore I can justifiably write that the energy is h bar squared k squared over 2m, because p is h bar k. Now here is where the expression of an energy for a free particle, and its energy regardless if it has an angular frequency omega. Therefore h bar omega must be equal to h bar squared k squared over 2m. This is how omega is connected to k for particles that exhibit a wave behavior, whereas this is the expression for pure waves, omega equals to kv, that derives off of the wave equation. This is a wave equation. So this one will give us a wave equation that justifiably can be written as such. Now, normal wave can be broken down into two harmonics, sine or a cosine, where basically, I mean, I know we can write it in terms of the wavelength x over lambda minus t over the period t, and t is actually equal to 1 over f, so this is ft, and I bring the 2 pi in there, so this can be written as either a sine or a cosine of 2 pi over lambda, which is kx, and also 2 pi over f over t, or 2 pi times f, and 2 pi times f is actually omega t. So it can be written in this form. I know, at least in my previous classes, we didn't use this form a lot, but this is how a harmonic wave would look like. So any other wave actually is a combination of these harmonics. We're going to do the same in here. We're going to require that psi for a free particle can be written as a combination of either a sine or a cosine of two harmonics with this wave number and also angular frequency, where A and B are going to be tweaked in a sense to make this work. What we want to work, we want it to be a wave, but mainly we want this expression between omega and k hold true. Omega is proportional to k squared, and there instead of omega is proportional to k only for the case of a normal wave. So how can we do that? Well, we can pull an omega out of this expression by just taking the derivative with respect to t, because we want an omega in here. We want an omega on this side. So we can take an omega derivative with respect to psi, derivative of psi with respect to t, and that should just free up an omega in here. If I use the chain rule, so I'm going to put a minus omega times a times the derivative of the cosine, which is just a minus sine of kx minus omega t. I know I have a bunch of parentheses in here. And the same thing in here, I'm going to put a negative in here, omega, so it's plus a negative omega times b, and the sign just switches to a cosine when we take its derivative. So it seems like we're almost in business. I mean, minus times minus is a plus, so I have an omega a times a sine of kx minus omega t, and I have a minus in here, omega times b, cosine of kx minus omega t. So this is almost that side. I have an omega. All I have to do is multiply this expression by h bar, and we're in business. So basically all I have to do is take this expression and multiply it by h bar at some point, not now, because I want h bar omega. So I have h bar omega in here, and I have an h bar omega in the second term. Let's find the k squared though. The k squared on the other side can be thought of taking the derivative with respect to x twice. Because if I take the derivative with respect to x, the first time I'm going to put a k in here, I'm going to put a k in here. If I take the second derivative with respect to x, I'm going to put another k, which makes it k squared, and another k in here, which makes it k squared. So let's do that. Let's take the first derivative with respect to x. And that, of course, the cosine will pick just a k in this case, a, and the cosine switches to a negative sign of kx minus omega t. And in here, I'm going to have a kb plus kb, and just the sign switches to a cosine. This is not hard to see. Now, if I take the second, remember I have a negative times ka in here. So if I take another derivative of the sign, I will put another k times k, that's k squared, and I still have a negative in here. So the second derivative of psi with respect to x will pull a negative k times squared times a, and sine switches to a cosine, kx minus omega t. And finally in here I have the cosine, which is going to flip to a negative sign, and I'm going to put another k with the existing k, so it's going to be negative k squared b, and sine of kx minus omega t. It seems like I have my k squared in here, and I needed it. So all I have to do is multiply by h bar squared divided by 2m. So I take this entire expression, both sides, and multiply them by h bar squared over 2m. And let's equate the two. Let's take h bar, its first derivative with respect to t, equal to this quantity. Now, there may be a problem in here, so we really need a fudge factor similar to what we did when we did the Lorentz transformations to make this work. So this is our fudge factor to make this whole thing work. What do we want to work? We want that relationship, that dispersion law, if you wish, between omega and k hold true. So we want this to be checking. So we want this to be true if we want any wave. That's what the physics led us to. So when we build the argument based on the experiments for the photoelectric effect and also the blackbody radiation and also Compton effect, this is where we were led to, how omega and k are related. And this is the math we're trying to build in here to make that work, to make the physics work. So my constant in here, C, is just to tweak things so that things work, okay, all the time. We don't want it to be working in a specific time or a specific place. We want this to be true no matter what X and T are. So H bar times this expression gives me H bar omega times A. I want to be careful in here with my signs. So it's a sine the first term, and the second time is a cosine with a negative sign. So it's, I just forgot. It's a sine of kx minus omega t. And the second one has a negative sign, h bar omega b, and it's a cosine kx minus omega t. This must be equal to c times h bar squared over 2m times this whole thing. Again, my c is just to make things work all the time. We don't want it to be working at some specific times. So minus c, because I have a minus in here, times the c, and I have an h bar squared k squared over 2m times a, and I have a cosine. So the first term is a cosine. I have a cosine of kx minus omega t, and the second term is a similar one, except I have a c h bar squared k squared over 2m times b now, and I have a sine of kx minus omega t. Well, we wanted h bar omega equal to h bar squared k squared over 2m, so we have to request that. We cannot, so these two terms are the same on both sides, so they cancel. Okay, that's a requirement. That's what the physics led us to. Okay, so what we were left with is a sine of kx minus omega t minus b cosine kx minus omega t is equal to minus c times a cosine kx minus omega t and minus cb sine kx minus omega t. We want this to be true everywhere and at any time. We don't want to be solving for a specific x or a specific t and then say it's true. No, we want it to be true all the time, which means that the coefficients of the cosine on both sides must match. And the coefficients of the sine on both sides also must match for this to be true. Which means that A must be equal to negative CB. That's one thing. And B and CA are the same thing. Not equal signs. B is CA. We want that to be true. Otherwise, we have a problem. So this is what we are led to. I mean, there is another justification. I know I was thinking about it. Some of you want more math rigor in this case. So what should you do in this expression to make this equations work? All you have to do is multiply by a sine of the same argument, sine of cosine kx minus omega t, and integrate over full period. It doesn't matter where your integration is going to be, either with respect to t or with respect to k. I mean, with respect to x. In either case, you're going to have the sine squared in here with a factor of 1/2, and also some constants that be pulled out from the integration. And this will be 0 anyway through a full period, because sometimes cosine is going to be periodic function up and down, so it's going to cancel out. And this one is going to be 0, and this one is going to be also that factor of 1/2. And at the end, you're going to get the constant CB with a negative sign equals to A, which is the first equation. The same thing, you do the same thing. You multiply by cosine, you eliminate this thing, and you eliminate that one, and at the end you're going just the coefficients of the cos squared and the cos squared and integrated over full period with within a constant of a k if you're integrating over x, or with respect to omega if you're integrating with a t. You're going to pull a 1/2, and that's going to cancel anyway, the 1/2 or whatever you pull from the integration, and so you're going to end up with a b equal to ca. So basically that's what we can do in terms of math rigor if you really want to. But sine and cosine are two orthogonal functions in this case, so you can just do whatever technique you want to argue that the coefficients must match. Anyway, so this is where we are led to. So A equals to negative C times B, but B is equal to CA. So what this is equal to is negative C squared A. So this is the equation that we have. Negative C squared A is the same thing as A. One way of making this happen is if you take A equal to 0. If A is 0, of course, this will work. 0 is equal to 0 no matter what C is. But that's a problem, because if A is 0, then that means that B also is 0. Remember, B is CA, so that B is 0. So and if A and B are 0, psi itself is 0. Remember, psi is just a linear combination of a cosine and a sine with A and B. But A and B are both of them 0, so we really don't have a psi. We don't have a wave mechanics, and we fail to produce this expression. We fail to describe for example, the double slit experiment for the electron. Therefore, this cannot be true. A cannot be 0. And by the way, B also cannot be 0. If B is 0, so is A too. So it's the same thing. So neither of them can be 0. So if that's the case, so A is not possible for it to be 0. The only thing is C squared must be negative 1, which means that C is simply equal to I. So that's what we are left with. Which means B is equal to CA is equal to IA. So this is how we have basically came up with. So this is where we are. Our C must be I, which means that this C in this expression must be I. So h bar, the first derivative of psi with respect to t, must be equal to I h bar squared over 2m times the second derivative with respect to x for a free particle. So this is where we ended up with. H bar, the first derivative of psi with respect to t, must be equal to c, which is I, times h bar squared divided by 2m times the second derivative of psi with respect to space. That's where we are. Now, this is not the normal way of writing this expression. We usually multiply in here by I, and we multiply by I in here, so this leads us, I times I is I squared, and that is negative 1. So this expression becomes I h bar, the first derivative of psi with respect to t is equal to negative h bar squared over 2m, the derivative with respect to the second derivative of psi with respect to x, plus, for the case of a particle inside a field of some sort, the potential of that field times the function size. This is the general equation, the Schrödinger's equation of a free, of a particle in 1D. I mean, psi is just a function of x and t. What is psi meaning? We're going to defer that. What is that I bar that popped up in there? That is actually something that is kind of strange for a function that is supposed to describe. That means psi itself is a complex number now, since we have I in here. So this is, the whole expression is a complex equation. So it's no longer a real equation. This is the equation that satisfies this connection between omega and k. This is, in a sense, how we can rationalize it, how we can justify, if you wish, the expression. This is not a full proof, okay? I'm just kind of this is not a proof. There is no proof for that. It's just like a law, like F equals to ma, okay? For quantum mechanics, of course. So let's go back into psi in here, because I just mentioned the fact that psi must be a complex number. Psi, I just said that it's A times cosine kx minus omega t. That's how we wrote it in the beginning for a free particle. Plus B times the sine. And B, remember, is just IA. So plus IA, or AI, times the sine kx minus omega t. Now if I pull an A out, of course it has the I in it, so it must be a complex number, but there is another actually form for it that we can write in here, which is a little bit more convenient. Cosine kx minus omega t plus I sine of kx minus omega t, And according to Euler's expression, this is nothing but the exponential of the argument of the trig functions. This is exponential of I times kx minus omega t, of course, times the a, and this is the wave function. Okay, so its interpretation and the meaning of the equation itself, of course, it's an energy equation, and you can clearly see that each bar has joules second, and you divide by second, so this is also must be an energy, so it's a joule. This is actually pure energy. This is a joule too. So whatever the units of psi are, which is a complex number, you have psi on this side times joules and psi on this side times joules. And so is this quantity actually. Each bar squared is a joule squared, second squared, divided by a kilogram and meter squared. Remember, a joule is a Newton squared, meter squared, second squared, divided by a kilogram, meter squared. I'm just doing dimensional analysis to make sure that this equation makes sense. Of course, the meter squared and the meter squared cancel, and the Newton squared is a kilogram squared, meter squared, divided by second to the power 4, because you have a Newton squared, which is a kilogram meter per second squared, and times second squared in here, divided by a kilogram. Second squared and second to the power 4, I'm left with the second squared, and I have a kilogram squared and a kilogram, so I ended up with, in terms of my dimensional analysis, as I need a joule, by the way, kilogram meter squared per second squared, and that is also a joule. Actually, it's a kilogram meter per second squared times meter, and this is a Newton meter. Newton meter is a joule. So again, just to make sense, to make sure that everything works, so this whole thing is a joule, this whole thing is a joule, and this whole thing is a joule, so it's an energy equation. We're going to build on that for the next video, and hopefully we're going to have more in-depth discussion of what this equation means, and we're going to actually be solving it for special cases. Thank you.